Okay, this is the review for chapters 2 through 6. Question 1, this is from the very beginning, very first day, finding the domain of various functions. So for part A, this is what's called a rational function. We studied a little more of these in section 3.6, but in chapter 2, the problem that we would run into with this type of function is what values of x would make the denominator equal 0. Remember, you can't divide by 0. So what we're going to have to do is factor the denominator. So 2 times negative 3, that's negative 6. We need two factors of negative 6 that add to negative 1. That's going to be negative 3 and positive 2. So to factor, we're going to have 2x squared minus 3x plus 2x minus 3. From this first grouping now, we factor by grouping. From the first grouping, we can take out an x. That leaves 2x minus 3. There isn't a common factor from the second grouping, so we can just pull out a plus 1. Leaves you with 2x minus 3. So those are the exact same factor, 2x minus 3. So that comes out as a common factor, 2x minus 3, and we would be left with x plus 1. So this is the function, and the denominator has now been factored. So we don't want the denominator to equal 0, so we need to figure out what values turn each factor into 0. So x plus 1 cannot equal 0, and 2x minus 3 cannot equal 0. This one, x cannot equal negative 1, and for this one here, x cannot equal positive 3/2. So those are the excluded values. X can equal anything except x cannot equal negative 1, x cannot equal 3/2. So says specifically though to use interval notation. So the domain would be negative infinity, negative 1, negative 1 to 3/2, 3/2 to infinity. Part B, a radical function, particularly square roots. Okay. With these square root functions in particular, you can't take the square root of negative values. So we need to ensure that whatever expression is inside the square root, in this case 3 minus 2x, it needs to be greater than or equal to 0. Now before I finish this, I want to directly compare this one to part C. Logarithms are a lot like square root functions in how you find the domain. You can't take the logarithm of negative values either, so to find the domain for part C, you take the expression inside the logarithm. The only difference is this one has to just be greater than 0, it can't equal 0. You can take the square root of 0, but you can't take the logarithm of 0. So to finish this one up here, if you subtract 3 on both sides, and then divide by negative, and then divide by 2, you have a domain of 3/2 to infinity. Whereas here, if you add the 8, divide by 2, since x is just greater than 4, the domain would be parenthesis 4 to infinity. Now, parts D, E, and F really comes down to recognizing what type of function each of these three are. For part D, 3x squared plus 5x minus 2, this is a quadratic function. The domain of any quadratic function is always all real numbers, or negative infinity to positive infinity. So if you recognize that the function is a quadratic function, automatically the domain is all real numbers. Same with part E. This type of function is exponential. Recognize that because the variable is part of the exponent, so this is exponential. Also has the same domain. As well as part F. Part F is a polynomial function. Remember the definition of the word polynomial. Poly means many, It's a function that's comprised of many terms, adding or subtracting. If you were to multiply both of these together, you'd end up with a long string of terms, you know, x to the fourth plus something all the way down. So this is a polynomial function. The domain of every polynomial function is also all real numbers, or negative infinity to positive infinity. So these types of functions here, functions in the form of a fraction, radical functions inside of a square root, or logarithm functions, these all had domain restrictions, whereas quadratic, exponential, and polynomial functions have no domain restrictions. So question 2, also from section 1 of chapter 2, supposed to evaluate the piecewise function, and the key here is this is still a function, meaning if you plug one number into the function, you should get one number out of it. Common mistake students make is to take the -3 and to plug it into all three pieces, but that would result in 3 different outputs for only one input, and it wouldn't be a function. So you got to make sure that you plug the -3 into the correct piece, and you have to look at these pieces of the function here. If x is less than 0, which -3 is, then you would plug that input into the top piece. So -3 plus 1 equals -2. For part B, an input of 0 fits into this middle piece here. Now that part of the function has no input. It only is ever going to equal 1, regardless of x is 0, 1, or anything up, but not including 3. So if you plug in a 0 into this middle piece, you're always going to get a 1. Okay, question 3. You need to recognize this symbol as composition of two functions. In this case, g goes into the f function. So the f function is the square root of x. And remember, when you're replacing x with other values, in this case another function, I always recommend that you turn all your x's into empty parentheses. So it's the square root of blank, and that blank gets filled in with 2 over x minus 1. And then if you're taking the square root of a fraction, you can separate the square roots into the numerator and denominator. So here we have the composition, but also asks for the domain. Now, this is a function in the form of a fraction, and remember, with fractions the denominator cannot equal 0. But also in the denominator we have a square root, and you can't take the square root of negative values. So we have 2 problems to worry about. So first of all, x minus 1 has to be greater than 0. It has to be greater than 0 because it's inside of a square root. And normally with square roots you would say it's greater than or equal to 0, but we don't want it to equal 0 because it's also on the bottom of a fraction. So x minus 1 has to be greater than, but not equal to 0. To finish solving this, just add the 1 to the other side, and x has to be any value greater than 1. So the domain is from 1 to infinity. Now for here, the other direction for the composition, this time f goes into the g function. So the g function is right here. It's 2 over an input minus 1. In this case, our input is the f function, square root of x. So that's our composition right there. Now for the domain, again, we have a couple of things to worry about. This piece of the function's in the denominator, so we don't want it to equal 0. But also x is inside of a square root, so we don't want x to be anything that's negative. So for just this piece right here, we would say that x has to be greater than or equal to 0. However, we still have to consider this minus 1. Right with this, what we're saying is x can be any number greater than and including 0. But there's one particular value. What if x equals 1? So if I plug the 1 in for x, the square root of 1 is 1, and 1 subtract 1 is 0. So we don't want x to equal 1. X can be anything greater than or equal to 0 except for the number 1. So the way we would state this using interval notation is from 0 to 1, parenthesis, union, 1 to infinity. Now for part C, we're adding the g to the h function. So 2 over x minus 1 plus 3 over x plus 3. These two functions can't be added to each other if they have denominators that aren't the same. So we need to get common denominators here. So now we have a common denominator of x plus 3 over x minus 1. This numerator, if it were simplified here, becomes 2x plus 6. And this numerator here, if it were simplified, becomes 3x minus 3. Now if we combine like terms in the numerator, 2x plus 3x is 5x, and 6 plus negative 3 is 3. So there's the composition. 5x plus 3 over x plus 3 times x minus 1. Now we again have to state the domain. This is a function that's a rational function, meaning it has a function in the numerator, it has a function in the denominator. It's the denominator that we need to worry about. X can't be negative 3, and x cannot be positive 1. Those would turn either of these factors into 0, and we can't divide by 0. So even though it doesn't say to put it in interval notation, I'm going to put it in interval notation. So from negative infinity to negative 3, from negative 3 to positive 1, and from 1 to infinity. For question 4, the original function here, the f function, has this equation, x squared, but then it was transformed into this function, the g function, so we've got to figure out what the transformations were. So first looking at the vertex, it started at 0, 0, and the vertex ended up being moved 2 to the left, and then up 1. And then the graph also flipped upside down. So g of x, first of all, in order for it to move 2 units to the left, a plus 2 needs to be inside the function. To move it up 1, a plus 1 needs to be outside the function. And then to flip it upside down, there's a minus sign. And it's important that the minus sign is outside of the function. This negative sign is outside the function. Okay, for question 5, part A and part B, we're finding an inverse. Finding an inverse basically has 2 steps. You switch the place of x and y, and then you solve for y. So, and remember, f of x can be thought of, f of x is just the same thing as y. So, first step, if we switch the place of x and y, we have x equals y plus 3 over y minus 1. So now when we try to solve for y, we have a problem here. We have 2 y's. So first we need to undo this fraction. So I'm going to multiply by y minus 1 on both sides. And then I'm going to distribute the x. But we still have 2 y's, and right now the 2 y's are on opposite side of the equal sign, so we need to get the y's on the same side of the equal sign. So I'm going to add this x over here and subtract the y over there. So it would end up with xy minus y equals x plus 3. The reason for getting the y's on the same side is we have 2 terms, each has a factor of y, so if you factor out the y, now we've gone from an expression with 2 y's to a single y factor, and you can divide the x minus 1 over, and this is the inverse. Now it just so happens, and this is just a weird circumstance or coincidence. But in this case, the inverse is exactly the same as the original function. That generally doesn't happen with these types of functions. But that was the case here. For part B, we start the same way. We can switch the place of x and y. So the problem we have here isn't that we have multiple y's. The problem here is we have a y that's an exponent, and we can't solve for y if it is an exponent. And the only way to make this not an exponent is to cancel the base. The only way to cancel the base is to use logarithm. So first step here would be to add the 4 to the other side. And now we can use a logarithm. Log base 3 to cancel the base of 3. So we have y plus 1 equals log base 3 of x plus 4. Final step is to subtract the 1 over. And this is the inverse. Now for part C, we've been given two functions, 2x minus 3 and x plus 3 over 2, and it's claiming that their inverses, f and g, are inverses we just need to show. Now I'm going to be kind of picky on a problem like this if it were to be on the final exam. The correct way to show that two functions are inverses, and this is the way that I'm going to accept for full points. The correct way to show that two functions are inverses is to really break this down into a two-part question. First thing you would have to find is f of g of x, and then second thing you'd have to find is g of f of x. And it's not just finding both compositions, it's what they equal that's important. So for the first composition here, if the g function goes inside the f function is 2 multiplied by an input minus 3. Rather than 2x minus 3, it's 2 multiplied by an input. The input is the g function, x plus 3 over 2. First is multiplying by 2 and dividing by 2. Those are inverse operations, so they cancel out, and you have x plus 3 minus 3. The plus 3 and the minus 3 cancel out, so it equals x. If we do the other composition, the f function goes inside the g function. The g function is an input plus 3 divided by 2, and here the input is 2x minus 3. I only use the parenthesis to make the substitution, but since there isn't a coefficient or an exponent here, parentheses aren't really necessary, so the plus 3 and the minus 3 cancel out, and we've got 2x over 2. The 2's cancel, and we'd be left with x. The important thing to show is that both compositions, f of g of x and g of f of x, both equal x. That's the correct way to show that two functions are inverses of each other. Okay, for moving into chapter 3 now. To show that this polynomial x minus 2 is a factor of this polynomial, we need to do a division problem and show that we get a remainder of 0. This would be much like showing that 3 is a factor of 12. One way to show that 3 is a factor of 12 is to do the division, and you get 4 with a remainder of 0. And that's the same thing we have to do here. We have to do the division and show that there's a remainder of 0. If there's a remainder of 0, that proves that whatever you were dividing by is a factor. So, since we're dividing by x minus 2, which is a degree 1 polynomial, we can use synthetic division. And key here is that we get a remainder of 0. So x minus 2 is a factor. Okay. Question 7, quadratic. Sketch the graph the graph of a quadratic function is a parabola, the most important part to find of the parabola is the vertex. So there's a couple ways you can do this. One way is to rewrite this from general form into standard or vertex form. That's done by completing the square. So if we start by moving the 4 over there to the side of the y, we're going to get y minus 4. And then the next step would be to factor out that leading coefficient of 3. So 3. If we factor out a 3, and remember the 4 is now gone to the other side, you're just going to be factoring out of the x squared term and the 6x term. So this is what's left over when you factor out a 3. And then remember there's a blank spot inside the parenthesis to complete the square. The value that completes the square is half of b to the second power. So if b is 2, half of 2 is 1, 1 squared is 1. But we've just created an unbalance here on the right side. I've added a 1 inside the parenthesis, but really that 1 turns into a 3 when you multiply it with this 3. So I've added a 3 to the right side, which means I have to add a 3 to the left side. So now we've got y minus 1. And this expression, x squared plus 2x plus 1, is factorable into x plus 1 to the second power. Add the 1 back over to the right side. And that's the same equation that we started with, it's just in a different form, standard form or vertex form. And you can tell by the transformations, this transformation of plus 1 moves the graph to the left 1 unit. The plus 1 on the outside moves it up 1 unit, so the vertex is at negative 1, comma 1. Next thing to find on a parabola is the y-intercept, or that's a reasonable thing to find here because the vertex is so close to the y-axis. You could really just start choosing any points and making a table, because right now we already know a point of negative 1 comma 1, that's the vertex, and you can just start choosing values that are near negative 1. But specifically I'm going to choose the y-intercept by letting x equal 0. So if I plug in a 0 for that x and a 0 for that x, I'm left with positive 4. And now you can use the fact that a parabola is symmetric. This would be the right side, because this has to be the bottom piece, so this is the right side. The left piece matches the right piece, so this point here gets reflected. That's a crappy looking parabola. Let's try that again. Okay, it's a little better. Even though I don't have it included here, I meant to include it. It's a really good idea for you to practice on this review. Anytime you make a graph, to state the domain and the range. So the domain, and this is what we talked about right at the beginning with the first problem, the domain of any quadratic function is all real numbers. The range, if you look at the range along the y-axis, the first point here, the lowest point, has a y value of 1, and the y values continue to increase up to infinity, so the range is from 1 to infinity. Now the other way you could do this is just to simply find the vertex. If you didn't want to complete the square, you can use the vertex formula, x equals the opposite of b divided by 2a, so you would have negative 6 divided by 2 times 3, which is 6, and you get negative 1. So you know that the x part for the vertex is negative 1, and then you can plug negative 1 back into the function. And if you plugged a negative 1 for that x and a negative 1 for that x, you'd end up getting a positive 1 out of that. So it tells you where the vertex is, negative 1 comma 1, and then you can go ahead and still find the y-intercept and reflect that point. Okay, question 8, polynomial function. There were a few steps here. If you look back through your notes for 3.2, the way I always did it when I was showing you problems like this is to find the zeros, and then the y-intercept, and then figure out the degree, because the degree can help you with the end behavior. So the zeros are found by the factors. Now, if the polynomial p of x wasn't in factored form, let's say it was all multiplied out into like x to the 5th plus something x to the 4th plus whatever, you'd have to write it in factored form like this and be able to find the zeros. But it's already factored, So we have a 0 of x equals -1. We have a 0 of x equals 2. With polynomials, it's also important to state what the zeros do. Do they cross or do they bounce? And it has to do with the multiplicity of the factor. So x plus 1 to the third power has a multiplicity of 3. Any odd multiplicity means that the 0 crosses through the x-axis. Now this factor, x minus 2, has a multiplicity of 2. Any even multiplicity means that the 0 or x-intercept bounces. So at -1 we're going to cross through, at positive 2 we're going to bounce off the x-axis. Now the y-intercept, if we let x equal 0, plugging in a 0 for that x and a 0 for that x, we're going to get 1 multiplied by 4, so we have 0, 4. Now the degree, if it's in factored form like this, where it's the parentheses multiplied together, the factored form is equal to either adding up the exponents or adding up all the multiplicities. We have a multiplicity of 3, a multiplicity of 2, that equals 5, so the degree is a 5th degree. Essentially what that means is the end behaviors are going in different directions on the left and right side. In this case, the left side's going down and the right side's going up. If there had been a minus sign in front of the polynomial, this would have switched to where the left side's going up and right side's going down. So anyway, left side's going down, right side's going up. Now, it's not, what we need to do now is, since we have a big enough gap between these 2 points and the y-axis and this point, you have a whole number value that's in between. I do expect you to plug in any whole number value to get a better and more accurate picture of the graph. So if I plugged in a 1 for x and a 1 there, 1 plus 1 is 2, 2 cubed is 8, -1 squared is 1, so when x equals 1, y is all the way up here at about 8. So down, it bounces there. Didn't quite hit that y-intercept very well. There it goes. But anyway, again, it'd be good practice on this review when you're graphing something to find the domain and range. And this goes back to, again, question 1. The domain of any polynomial function is all real numbers. And for this one, the range, this graph continues down to -infinity. It also continues up to positive infinity. So eventually, any number on the y-axis, you could find a point corresponding to that number on the y-axis. So the range is also all real numbers. Okay, question 9. The key here is to recognize what type of function this is. -16t squared plus 96t plus 64 is a quadratic function, and since there's a negative leading coefficient, that means it's going to be an upside down parabola. And if you look at the variables, t stands for time, and that's normally where x goes, so we know that along the x-axis we have time, and then it's h of t, where h means height, so the y-axis is height. So it's asking us to find how many seconds does it take to reach the maximum height, and what is the maximum height? Well, if this is the height and this is time, then the maximum height is just a vertex. And the key word here is maximum of an upside down parabola means finding the vertex. It's really a very simple problem if you understand what it's asking and if you understand what kind of function you have here. It's a quadratic function. Keyword maximum meaning find the vertex. And luckily we've already been given the function. So to find the vertex, I'm going to refer back up to this problem here. To find the vertex of this quadratic function, we could either complete the square or simply use the vertex formula. It might be a little quicker to use the vertex formula. So instead of x equals, I'm going to say t equals the opposite of b divided by 2a, which is -96, divided by 2 times -16. 96 divided by 32 is 3, and since we're talking about time here, this is 3 seconds. So that answers this question: how many seconds does it take the ball to reach its maximum height? Now we actually need to find the maximum height. So the height at 3 seconds is equal to plugging in the 3 for t, and let's see, 3 squared is 9, 9 times negative 16 is negative 144, and 96 times 3 is 270, 288, plus 64. So this is 144 plus 64 is 208 feet. That's the maximum height. Okay, question 10, finding all the zeros of a polynomial. We've done quite a few of these back in chapter 3 and as bonus questions on many of the exams. Starts with the p and q. The list of p are the factors of your constant at the end. So it's plus or minus 1, 2, 3, 6, 9, and 18. Q are the factors of the leading coefficient, which is 1. And what we're really getting after is p divided by q. But since q is 1, if you divide anything in p by 1, all you end up with is the value in p that you started with. So that's our list right there. So remember, this is just a list of possible zeros. The polynomial itself only has 4 zeros, so there's way too many numbers here that all of these could be zeros. So you just start picking some and test them using synthetic division. So I'm going to test positive 1. And see if we get lucky. And it looks like we do. So this has proof that x equals 1 is a 0, but it's also given us 2 factors. Anytime you perform division and get a remainder of 0, you get 2 factors. This is a factor right here, x minus 1, but that's also a factor right there. So I'm going to rewrite the polynomial into its 2 factors, x minus 1, and this is a reduced polynomial. We started with an x to the 4th, so then this is the leading term of, or the leading coefficient of an x to the 3rd, plus 2x squared, plus 9x, plus 18. Now, we found 1 0, that means there are 3 to go, so I'm going to go back to this list. But when I test numbers from this list, I'm going to test them on this reduced polynomial here. So, because I have done this problem before, I know that negative 2 is a 0, but you might have to go through a few more before you actually find that. But to save time, go ahead and do the synthetic division, and that proves that negative 2 is a 0, and it's also provided us with an additional factor here. So I'm going to rewrite p of x one more time with x minus 1, x plus 2, and then the reduced polynomial. Now if it's reduced from an x to the 3rd, it reduces to x squared plus 9. Now we have found 2 zeros from these 2 factors. There are 2 more to go. They're going to come from this quadratic factor. Now once you've reached a quadratic factor, and I know it's quadratic because it has an x squared, square is the highest exponent. Once you've reached a quadratic factor, you don't have to refer back to this list any longer. You can solve the quadratic as if it were a quadratic equation. So generally, when you're left with a quadratic factor, you're going to either factor it using normal factoring techniques, or you're going to use a quadratic formula. However, this one is kind of special. There's no middle term. We have an x squared term and a constant. If that's the case, you can solve for the zeros by setting it equal to 0, moving the constant to the other side, and taking square root on both sides. if there had been a middle term like 5x or something like that, you would have either had to use the quadratic formula or factored it. So anyway, we have all of our zeros now. X equals 1, x equals negative 2, and x equals plus and minus 3i. The problem also asks us to write p of x in its fully factored form with all 4 factors. Okay, question 11, section 3.6. The directions here are kind of a direction here of where you should head and some of the steps that need to be taken. I always start these problems by finding the asymptotes first. So the vertical asymptote of a graph is there because of a domain restriction. And with these types of functions, the domain restriction comes from the denominator. So you're going to want to look at the denominator in factored form, x plus 2, or in this case, x minus 2, x plus 2. X can't be 2, x can't be negative 2. So those are the vertical asymptotes. X equals plus or minus 2. The horizontal asymptote is easy to find, but you have to remember how to find it because it's different depending on what the problem looks like. If you have the same degree of the numerator and the same degree in the denominator, then you look at the leading coefficients and divide them. Let me repeat that. If you have the same degree in the numerator and the denominator, then you divide the leading coefficients to find your horizontal asymptote. 1 divided by 1 is 1, so the horizontal asymptote is at 1. Next I'm going to find the intercept. So starting with the y-intercept, you always let x equal 0 to find a y-intercept. So if that x is 0 and that x is 0, you're going to get 0 over negative 4, which is 0. The shortcut for finding the x-intercept on these particular functions, well, let me back up. The way that you find any x-intercept is to let y equal 0. So if we plug a 0 in there for y, we've got to figure out what turns this fraction into 0, or this rational function. And the shortcut here is just to consider what makes the numerator equal 0. The only way a fraction is ever going to equal 0 is if the numerator equals 0. And x squared is only ever going to equal 0 when x is equal to 0. So we get the same point for the x and y intercept. Now we've got to figure out what this graph looks like. So if we come over here to the region on the right, we have two options. Either the graph is contained in the top portion there, or it's contained in the bottom portion. It can't be contained in both the top and the bottom because it wouldn't pass a vertical line test, it wouldn't be a function. But it can't be contained in this bottom portion because there's no x-intercept anywhere here to allow the graph to pass through the x-axis. So this piece of the function has to be up here in the top right corner. The same argument can be made over here on the left. We have the same two options. Either the graph looks something like that, or the piece looks something like that, but there is no x-intercept here to allow the graph to pass through the x-axis, so it has to have that kind of a shape on the left side of the graph. Now, in the middle, it's not quite as obvious or straightforward where the graph is. You know what, it might look something like that, or you know, it might look something like that, or it could be something where it's, you know, a parabola. So to be sure, we ought to test some points. So I'm going to test a -1, I'm going to test a +1, see what happens in the function. So if I plug in a +1 for both x's, 1 squared is 1, 1 minus 4 is -3, 1 divided by -3 is -1/3, and if I test -1 for both x's, I get -1 squared, which is 1. Here I get -1 squared, which is 1. 1 over 1 minus 4 is -1/3. So this shows that kind of behavior in the middle. For part B, I'm going to want to factor the denominator again, like on part A. And this is going to factor into x minus 4 and and x plus 1, x minus 4 here, and x plus 1 there. So looking at the denominator in factored form, we see that x can't be 4. So we place a vertical asymptote there. And then x can't be negative 1. So we place a vertical asymptote there. So vertical asymptote at negative 1, vertical asymptote at positive 4. Now, this case for the horizontal asymptote is a little different because this is a degree 1 polynomial, this is a degree 2. Anytime the numerator has a smaller degree than the denominator, that means the horizontal asymptote is at 0, right along the x-axis. Now the y-intercept, again we find by letting x equal 0. If I plug a 0 in for all of the x's, I get 0 minus 1, so that's a negative 1 over negative 4. It's positive 1/4. It's about right there. If I want to find x-intercepts, then I let y equal 0. And quite often you can get more than one x-intercept. So if I let y equal 0 right here, the only way that's going to happen is if the numerator itself equals 0. The only way the numerator is going to equal 0 is when x equals 1. So when x equals 1, y equals 0. There's our x-intercept. So now we've got to try to figure out where the graph is. And starting over here on the left, either we have a graph or a piece of the graph that looks like that, or it may look something like that. And because the horizontal asymptote is right on the x-axis, it's not quite as clear as just looking at it and making a decision, so we need to test a point. If I chose negative 2 as a test point and plug negative 2 in here, negative 2 minus 1 is negative 3. Negative 2 minus 4 is negative 6. Negative 2 plus 1 is negative 1, but when you multiply you get positive 6. That's negative 1/2. So negative 2 comma negative 1/2. Then if I were to plug in a 5, I'm gonna go over here now to the right. Well, let me finish this up. If on the left side of this vertical asymptote, if one point is underneath the horizontal asymptote, or the x-axis for that matter, all of them are. This kind of a situation isn't going to be possible because it would have to cross through the x-axis, and there is no 0 there or x-intercept to allow it to do that. So that whole entire piece, if there's a point underneath, all of the points are going to be underneath on that piece of the graph. Now, coming over here to the right side, we're going to do a similar thing. I'm going to plug in a 5 as a test point. 5 minus 1 is 4. Down here, 5 minus 4 is 1. 5 plus 1 is 6. 1 times 6 is 6. That's 2/3. So 5 comma 2/3. That also tells us the whole portion of that graph is above the x-axis. It can't go below the x-axis because there aren't any zeros to allow it to pass below the x-axis. Now, over here we know that the graph passes through the y-axis, and it also passes through the x-axis, and we know it crosses through and not bounces because this is where the 0 came from, and it has a multiplicity of 1. So here, if we try to continue, the behavior of a graph as it nears a vertical asymptote is to either go up to positive infinity or to go down to negative infinity. But this graph isn't going to turn down and go to negative infinity, because in order to do so it would have to cross through the x-axis. There isn't a 0 down here to allow it to do that, so the only direction it can go is up to positive infinity. And similar argument here, as the graph approaches this vertical asymptote, here on the left side it's either going to continue to negative infinity or it goes up to positive infinity. Those are the only two options. Either it goes up to infinity or down to negative infinity. But if this graph were to turn up and go to positive infinity, it would have to pass through the x-axis again. There's no 0 there, so it continues down to negative infinity. Okay, for question 12, we've got two exponential functions. A couple of things to remember about exponential functions, at least in how you graph them. Exponential functions have horizontal asymptotes. If there aren't any transformations on the graph, then usually the horizontal asymptote is right here on the x-axis. However, we have that transformation right there of +2. +2 occurs outside the function, which means it's going to move the graph, in this case, up 2 units. So the horizontal asymptote is up 2 units from the x-axis. Okay. The only other thing we need to do now is to find a couple of points on the graph. One of those points needs to be the y-intercept, and you find that by letting x equal 0. 0, if you plug in a 0 right here for this x, 0 minus 1 is -1. 2 to the -1 power is 1/2. 1/2 plus 2 is 2.5, so the y-intercept is right here at 2.5. And then at this point, since the domain of any exponential function is all real numbers, you can choose any x values you want, but I'm going to keep it simple and choose some smaller values. In this case, x equals 1. If x equals 1, 1 minus 1 is 0, 2 to the 0 power is 1, 1 plus 2 is 3, so the point 1, 3 is on the graph. I'm going to choose one more here. If x equals 2, 2 minus 1 is 1, 2 to the first power is 2, and 2 plus 2 is 4. So the graph looks something like that. Let me try that one more time to get a little better picture. It doesn't touch the y, or it doesn't touch the horizontal asymptote. It just keeps getting closer and closer to it. The domain is all real numbers. As a matter of fact, I should have put the range on here as well. The graph doesn't go below the horizontal asymptote in this case, so this line 2 acts as a barrier. So the range or y values start at 2, not including 2. Notice it's parenthesis. 2 to infinity. Now part B, this -1 on the outside of the function means that the whole graph, including the horizontal asymptote, moves down 1 unit. And then doing what we did over here, finding a few points, one of them being the y-intercept when x equals 0. If x equals 0, 1/3 to the 0 power is 1. 1 minus 1 is 0. Now, this base right here, a base of 1/3, anytime you have an exponential function that has a base that's smaller than 1, that means you're going to have exponential decay, meaning the graph's going to start up here and decrease as it gets closer and closer to this horizontal asymptote. Knowing that the graph is going to be up here in this region, I'm going to choose some negative values of x to see where the graph is over here. I'm going to choose -1. 1/3 to the -1 is 3, and 3 minus 1 is 2. So the point -1, 2 is on the graph. I'm going to do one more point here, -2. If I plug in a -2 for x, 1/3 to the -2 power is 9. 9 minus 1 is 8. So -2, 8. The domain of any exponential, whether it's a decay function like this or a growth function like that, the domain is all real numbers. Range for this one is from -1 to infinity. Okay, question 13, evaluating a logarithm. I'll show you two different ways. The way this can be done without a calculator is to try to get matching bases. Here we have a base of 3, so the goal would be to change 81 into 3 to some power. So 81 is the same as 3 to the 4th power. Now that you have matching bases, the logarithm cancels out the base, and you're left with 4. The other way to do this is simply to use a calculator, but most calculators can't do any logarithm with a base other than 10. So you'd have to plug this in using the change of base formula. The log base 3 of 81 on a calculator could be plugged in as log of 81 divided by log of 3. If you type that in correctly, it should also tell you the answer is 4. So over here on part B, we've got to match up a base of 25 with a logarithm and turn this into 25 to some power. So 5 is the same as the square root of 25. So we're getting closer to matching bases, but it's only a base if it has an exponent. But a square root is the same as an exponent of 1/2. So now we have matching bases, and we get an answer of 1/2. But this could also be done on a calculator as log of 5 over log 25. That will also equal 1/2. Now part C here, natural log, remember, is just a normal logarithm that has a base of e. It's just not written. So if this natural log has a base of e and this exponential term has a base of e, then the natural log and the base e just cancel each other out. And the answer is 3. Not much work there. Okay, question 14. Using the laws of logarithms to expand or condense. So on part A, we have a single logarithm that needs to be expanded into several logarithms. And if you look at what's inside the logarithm, each factor here is being separated by a multiply, where they're all multiplying together. That means that each logarithm needs to be separated by a plus sign. When you expand a product, you use plus. You add the logarithms together. And then the final step would be to move the exponents down to the front of their logarithm. So 2 log base 4 of x plus log base 4 of y plus 3 log base 4 of z. Part B, we're going the other direction, where we have several logarithms that we need to eventually condense into a single logarithm. First step is to look at all these numbers in front of a logarithm and realize that they were exponents, so we need to move them back up as exponents. Log of x to the third minus log y to the fourth plus log of z squared. Now, I'm going to take these two logarithms here and condense them. And since there's a minus sign between the two logarithms, when you condense into a single logarithm, you use division. Now, you can condense these two logarithms. Since they're separated by a plus sign, when you condense the two logarithms, you need to multiply the terms inside the logarithm. So x cubed over y to the fourth multiplied by z squared. The z squared is going to multiply the numerator, so you're going to end up with log of x to the third z squared over y to the fourth. Question 15. We're solving for x, but x is part of an expression that's inside of a logarithm, and you can't solve for x if it's inside of that logarithm, so we're going to have to cancel that natural log. The only way to cancel the natural log is to eventually use a base of e, but that's not going to be our first step, because we need this logarithmic term to be by itself, so we actually need to add the 2 over. Now we can cancel the natural log by using a base of e on both sides. And then subtract the 3. So this is the exact answer, e to the 5th minus 3. I would also like you to plug that into a calculator to give me the approximate answer. So x, if you do e to the 5th, and subtract 3, you're going to get 145.41. Now over here on part B, if you have two logarithms on the same side of an equation, you can't solve the equation unless you condense the two logarithms into a single logarithm. Now since the logarithms are separated by a plus sign, I'm going to use multiplication. So x times x minus 2 equals 3. Now I'm going to distribute the x there, so I've got log base 2 of x squared minus 2x. Okay, we're solving for x in an expression that's inside of a logarithm, so we've got to now cancel the logarithm. You use a base to cancel a logarithm, base of 2 in this case. So now we've got x squared minus 2x is equal to 8. Well, this is just a quadratic equation, so you got to get it equal to 0 by subtracting 8. This factors into x minus 4 times x plus 2, which means right now we have solutions we're looking at of x equals 4 and x equals negative 2. However, you need to remember that for logarithms, you can't take the logarithm of a negative value. If I were to plug negative 2 into either that x or that x, it would result in taking the logarithm of a negative value, which is no good. So the only answer is x equals 4. For question 16, we're solving for x, but x is a variable that's part of an exponent, and you can't solve for a variable if it's an exponent, so we need to cancel the base eventually so that the x plus 2 is no longer an exponent. But we can only cancel the base if this expression, or that part of the equation, 2 to the x plus 2, is by itself. So you got to add the 1 over. So add 1, 4 times 2 to the x plus 2 equals 12. Now divide the 4. We get 2 to the x plus 2 equals 3. So now we've got 2 to the x plus 2 by itself. We can cancel the base of 2 using log base 2. So now we've got x plus 2 equals log base 2 of 3. And then we can subtract the 2 to the other side of the equation and get x equals log base 2 of 3 minus 2. And I would also expect this to be given in decimal form, so you have to plug this into your calculator. So log base 2 of 3 minus 2 is negative 0.415. Okay. If you're trying to model a situation that you know is exponential, exponential means it's increasing or decreasing the same factor or the same rate. So this is getting cut in half every 4 days, so it's decreasing by a factor of 1/2. That means it's exponential. If it was something that was doubling every so often, like bacteria or populations, if it's being multiplied by the same number every so often, in this case multiplied by 2, that's also exponential. If you can recognize the situation as exponential, then it's going to be modeled using an exponential function. In this case, the one we learned back in chapter 4 was the initial amount a sub 0, and then the base had to do with what's happening in the problem. If it was being cut in half with a half-life, then the base was 1/2. If it was doubling, like a culture of bacteria was doubling, then the base would be 2. The exponent is t for time divided by x, where x is the amount of time that it takes to be a half-life, or the amount of time it takes to double if this were another situation. And in this case, x is 4 days. Our initial value is 10 grams, so our function a of t is equal to the initial mass, 10 grams, multiplied by 1/2 to the t over 4. The reason for part A, finding the function, is you can use the function now to find out how much of the substance remains after 5 weeks. But this function was built using a time value of 4 days, so we can't mix weeks with days, so 5 weeks is equal to 35 days. So the amount remaining after 35 days if we were to plug this into a calculator, we get 0.023 323 grams. Okay, we've got three kinds of tickets here. There's a matinee, there's a student, and there's a regular. So there's three different types of tickets, which means we're going to have three variables here. Let x equal the number of matinee tickets, let y equal the number of student tickets sold, and let z equal the number of regular tickets sold. If we have three different variables, we have to come up with three different equations that relate the three variables together. So looking at this one, the first phrase here, the total ticket sales were 8,500 movie tickets. That number 8,500 is a result of adding the number of matinee to the number of student to the number of regular tickets sold. So it would be x plus y plus z equals 8,500. The next phrase here, or sentence, proceeds totaled $64,600. The total amount of money earned is a result of $5 times the number of matinee tickets x, so $5 times the number of matinee tickets plus $6 multiplied by the number of student tickets plus $8.50 multiplied by the number of regular tickets. That's going to give you total proceeds of $64,600. Now, difficult phrase might be this last one. Twice as many student tickets were sold as matinee tickets. So student tickets are y, and matinee tickets are x. So we got to figure out some way to relate these two with an equal sign. Twice as many student tickets were already sold, so y is already twice as big. So in order to make these two quantities equal each other, I've got to multiply the x by 2. So y is equal to 2x. And I'm going to change this and move the 2x over and say negative 2x plus y is equal to 0. So if you notice this bottom equation, z is already missing from the bottom equation. And I have an equation in terms of x and y. So if I take the first two equations that I made, if I take the first two equations and eliminate the z variable, that's going to result in an xy equation that I can combine with this xy equation. So what I'm going to do is multiply top equation by negative 8.5. That's going to allow me to eliminate the z variable. So negative 8.5x minus 8.5y minus 8.5z equals 8,500 times negative 8.5 is negative 72,250. Middle equations staying the same. When I combine these, the z's cancel. I get negative 3.5x minus 2.5y is equal to negative 7,650. So now if I take this result and combine it with this result, so I'm just going to move this equation over to here. So now I can try to eliminate another variable. So if I multiply the bottom equation now, and I'm talking about this bottom equation, if I multiply that by negative 2.5, I'm going to eliminate the y variable. So negative 2.5 multiplied by 2 is 5. So let me rewrite this here. Bottom equation is now 5x. Actually, this needs to be plus that's going to be negative 5x plus 2.5y equals 0. So now the y variable's gone. We have negative 8.5x equals negative 7,650. And you divide 7,650 by 8.5, the x value is 900. That means there were 900 matinee tickets sold, and it says twice as many student tickets were sold, so that means there were 1,800 student tickets. And there were only 8,500 tickets that were sold that day, so if you add 1,800 and 900, that's 2,700. If you take 2,700 from 8,500, you get 5,800. Okay, question 19, partial fractions. There are three factors. X plus 1 squared counts as two factors. Since there are three factors, we need three pieces, or three partial fractions. And since x plus 1 is a repeated factor, then the partial fractions are written this way. The first time the factor is written, it doesn't have the power, and then the power increases until you match the power here to the power here. So there's three pieces here, or three partial fractions. The next step is to multiply both sides by the LCD, which is x times x plus 1 squared. That cancels the denominator on the left side, and you get 3x plus 2. Over here on the right side, when the LCD multiplies to all three partial fractions, when the LCD multiplies to the a partial fractions, the x's would cancel, and you get a times x plus 1 squared. When you multiply the LCD to the b partial fraction, this x plus 1 cancels with only one of these x plus 1s, so b multiplies in x and in x plus 1. And then when this LCD multiplies to the c term, the x plus 1 squared cancels with this x plus 1 squared, so c multiplies with x. So we're solving for a, b, and c. We're not solving for x. Because we're not solving for x, we can allow x, in this equation here, we can allow x to equal any value that we want. So now we choose what we talked about in 5.3 were called convenient values. We have way too many variables to solve for in just one equation. We have a, b, and c. But if we can cancel out part of this equation, leaving a single variable to solve for, that'll be much easier. So the convenient value, one of them in this case would be x equals negative 1, because if I plug in negative 1 into this right here, this x, negative 1 plus 1 is 0, so that cancels the a piece. If I plug in a negative 1 for this x, negative 1 plus 1 makes that factor 0, so that's going to cancel the b piece. I'd just be left solving for c. So if I plug in a negative 1 into the left side of the equation, you get negative 3 plus 2, which is negative 1. The a term is gone, the b term cancels out, c times negative 1 is negative c, so we get c equals 1, simply by conveniently choosing to let x equal negative 1. I'm going to do it one more time to find another value. I'm going to let x, in this case, equal 0, because if I let this x here equal 0 for c, c is gone. If I let this x here by b equals 0, then 0 times b means the b disappears, and we'd be left solving for a. So, plugging in a 0 for this x, 3 times 0 is 0, 0 plus 2 is 2. Over here, 0 plus 1 is 1, 1 squared is 1, 1 times a is a. The b term disappears, the c term disappears, so we know that a equals 2. Those were the only two convenient values of x, negative 1 and 0, but there's still one more value to solve for. We haven't solved for b. So if you have run out of convenient values, you need to just start plugging in random values for x. So I'm going to let x equal 1. It's not going to cancel out either a, b, or c. And because of that, you need to also plug in the values that you know up until this point. A equals 2 and c equals 1. Plug them all in. So if x equals 1 on the left side, 3 times 1 is 3 plus 2 is 5. And if a equals 2 and x here is equal to 1, 1 plus 1 here is 2. 2 squared is 4. 4 times 2 is 8. We don't know the value of b, but we're choosing to let x equal 1. So that x is a 1. That x is a 1. 1 plus 1 is 2. 2 times 1 is 2. 2 times b is 2b. And then over here, we already found that c is equal to 1, and we're letting x equal 1. 1 times 1 is 1. 8 plus 1 is 9. If you subtract the 9 over here from this side, you get negative 4 equals 8, or negative 4 equals 2b. So b equals negative 2. So we now know the values of a, b, and c, so we complete our partial fractions as 2 over x plus negative 2 over x plus 1 plus 1 over x plus 1 squared. Now for number 20, even just because it says calculate a times b, you ought to check to see if it's even possible. The way that you determine if you can multiply two matrices is to look at the size or dimension of the matrices. So this one is a 3 rows and 2 columns, so it's a 3 by 2. This one has 2 rows and 2 columns, so the inside dimensions here are the same, which means the multiplication is possible. The outer dimensions tell us that we're going to end up with a 3 by 2 matrix. So one way I suggested that you can do this problem is to set it up like this. And then you write the resulting matrix down here. If it's a 3 by 2 matrix, it's going to have 3 rows with 2 columns like this. So this first entry in the top left corner is a result of this top row and this first column combining. So this row combining with this column, 2 times negative 3 is negative 6, and then 4 times 4 is 16. This entry is a result of combining this row to this column, so negative 1 times negative 3 is 3, negative 3 times 4 is negative 12. This entry is combining this row with that column, 0 times negative 3 is 0, negative 2 times 4 is negative 8. This entry here, top right, combines this first row with that first column, so we get a negative 2, and 4 times negative 2 is negative 8. Here, we're going to have a positive 1 and a plus 6. And then this entry is going to be a 0 and a plus 4. So it looks like we're going to have 10, negative 9, negative 8, negative 10, positive 7, and positive 4. Okay, question 21. To find the determinant of a 3 by 3 matrix, it could be done a number of different ways. Easiest way is to choose a row or a column that contains a 0, like this column, for example, there's a 0. And then keeping in mind this pattern of pluses and minuses in a 3 by 3 matrix. So if you're choosing the first column here, you're going to have to follow this kind of a pattern. Once you've chosen a column, then you have to find the cofactors. So if I cross out the row and the column there, and then plus just means it stays positive, so I'm going to use 2 multiplied by the resulting minor of negative 6, 1, 2, negative 3. Cross out that row and column, and this 3 here is in that spot where the minus sign is, so it's minus 3. multiply by the minor 0, 3, 2, negative 3. And now cross out that row and that column. And since it's in this spot, you follow the plus 0, multiplied by this minor 0, 3, negative 6, 1. And the reason for choosing a column containing a 0 is 0 multiplied by that minor is 0. So that piece of this expression goes away. Now, these aren't just matrices. This is a determinant. You need to find a determinant here. So to find the determinant of a 2 by 2 matrix, it's this cross product, negative 6, or this multiplication, negative 6 times negative 3, which is 18, minus the other multiplication, 2 times 1. And here we got minus 3, and then the determinant of this 2 by 2 matrix is going to be 0 minus 6. 2 times 16 minus 3 times negative 6. This gives us 32 plus 18, which is 50. Okay, question 22 wants us to solve this using two different methods. So first of all, matrix equations. So right now we have a system of equations. We need to change these into a matrix equation. So the first matrix is the matrix containing the coefficients. The second matrix is a matrix containing the variables, and the third matrix is a matrix containing these constants 3 and negative 8. Remember, symbolically we represented this back in section 6.3 as A times X is equal to B. And we're solving for X, and the only way to get X by itself is to get rid of A. But remember, A represents a matrix, and you can't divide by a matrix. There's no such thing as dividing by a matrix. But you can multiply it by the inverse of a matrix to cancel it out, which means you also multiply by the inverse over here. So what we need to find is X is equal to the inverse of A times B. We know what B is. B is right here. 3 and negative 8. We need to find the inverse of A. So the inverse of A is this formula here. You switch the place of A and D, and then B and C become the opposite values, and then it's 1 over AD minus BC. It's 1 over the determinant, basically, of a 2 by 2 matrix. So 1 over negative 2 minus 15. Negative 2 minus 15 is negative 17. And then if you switch the place of A and D, we're going to have a negative 2 here and a positive 1 there. And then B and C switch signs to negative 5 and negative 3. So this is the inverse right here. And according to this, we multiply the inverse by the B matrix. So I'm going to take this inverse of A and multiply it by the B matrix, 3, negative 8. You can see what that results in. Now notice I'm going to leave the negative 1/17 out of this matrix. I'm going to multiply these two matrices first, and then I'm going to take the negative 1/17 and multiply it into that matrix. So this entry comes from combining this row to that column, so I'm going to get a negative 6 and a positive 40. This entry is a result of this row with that column, so that's a negative 9 and a negative 8. Negative 6 plus 40 is 34, and then negative 9 minus 8 is negative 17. Now take this negative 1/17 and multiply it into there. And we get negative 2 and a positive 1, so the answer for part A is negative 2, 1. Now since we're solving the same system of equations again, we should expect to get the same answer. We just solve it using a different method. For part B, we use Cramer's rule. Cramer's rule is essentially just finding a bunch of determinants, and then once you have found the determinants, the x value is d sub x divided by d. The y value is d sub y divided by d. So d is the determinant of just a coefficient matrix. 1, 3, 5, -2. Remember that you find the determinant of a 2 by 2 matrix by multiplying first here, -2, and then subtracting the other product, 15. That results in -17. The d sub x, the subscript says that this x column is going to be replaced. So instead of a 1 and a 3 in the x column, you take these values here, 3 and -8, and place those in the x column, and find the determinant. So it's 3 times -2, it's -6, minus this other product of -40. That results in 34. Here the d sub y determinant, the subscript y, means that the y column now gets replaced with the 3 and the -8. The x column stays the same as it originally was, 1, 3, and we find the determinant here by multiplying there, -8, and then subtracting the other product, and we get -17. So d sub x was -17, or sorry, d sub x was 34 and d was -17, so we get an x value of -2, and then here for y, d sub y is -17, and d is also -17, so we get a y value of 1, so the answer again is -2, 1. Okay, 23 says solve the system of equations by writing the system as an augmented matrix and reducing the matrix to row echelon form, or use Gaussian elimination. That means the same thing. So to use Gaussian elimination, the first step is to write the augmented matrix. And then use row operations to reduce this into row echelon form. Remember, that's where you have 1, 1, 0, 0, 1, 0, and a 1. So we already have a 1 here, which is nice. The next task then would be to get a 0 and a 0. So if I want to turn the 3 into 0, then I could make the 1, I could multiply the 1 by -3 and add them together. So I'm going to multiply -3 to row 1, add that to row 2, and that's going to become my new row 2. And then using the same arrow, I'm going to do one more row operation. I want to get this value here also to be a 0. So if I refer back up to the top row and multiply it by -2, so -2 times row 1, if I add that to row 3, that's going to be replacing my row 3. So following this first row operation here on top, -3 times 1 is -3, -3 plus that 3 results in a 0. Now move over to the next term, -3 times this 3 is -9, -9 plus -2 is -11. Now moving over here, -3 times 6 is -18, plus 3 is -15, and then here -3 times -3 is 9, 9 plus 8 is 17. Now follow this row operation down at the bottom. -2 times 1 is -2, -2 plus 2 is 0. -2 times 3 is -6, -6 plus 6 is 0. Here we get -2 times 6, which is -12, -12 plus 12 is 0, and here we get -2 times -3, which is 6, 6 plus -6 is 0. So this is a somewhat unusual circumstance where this bottom row is all zeros. It still represents an equation, but it just represents the equation 0 equals 0. I know you've seen that before. When 0 equals 0, that means infinitely many solutions. And according to this, if there are infinitely many solutions, we have to state the solutions in terms of a parameter, or parameterize the solutions. If there are three equations with three variables, which there are, the convention is to let z equal the parameter t. And then we got to find the value of y. Y can be found from this middle row of the matrix. Negative 11y minus 15z is equal to 17. But we know that z is now equal to t, so this is negative 11y minus 15t equals 17. We already know that t is equal to z, so we don't need to solve for t again, we need to solve for y. So I'm going to move the 15t over by adding it, and then divide everything by negative 11. So y equals negative 15t over 11 minus 17 over 11. So there's the value of y. So we have the value of z, we have the value of y, we just need the value of x. The value of x can be found from the top equation now, x plus 3, but instead of 3y, I'm going to replace the y with the value we know, negative 15t over 11 minus 17/11, and then plus 6. Normally that would be a z, but z is equal to t, so it's plus 6t equals negative 3. So if you distribute the 3, you're going to get x minus 45t over 11 minus 51 over 11 plus 6t equals negative 3. Now we've got some like terms to combine. The 6t and the negative 45t over 11 need to be combined, but you have to add fractions with a common denominator, so this becomes 66t over 11 if you combine, or if you multiply by 11 over 11. So if we now combine here, 66t minus 45t is 21t. Over 11, and I'm going to go ahead and add the 51/11ths over to this side, but you can't add 51/11ths to negative 3, they don't have the same denominator, so this could become negative 33/11ths. So if you add 51 to negative 33, you're going to get 18, so this is 18/11ths. Subtract the 21t/11ths to the other side, and you get x equals negative 21t/11ths plus 18/11ths, and there's your value of x. So the parameterized solution is x comma y comma z, so it's negative 21t/11ths plus 18/11ths. There's your x value. Your y value is negative 15t/11ths minus 17/11ths, and then your z value is t. Gotta love those fractions. Okay, question 24 is solving nonlinear system of equations. Notice here that we can eliminate the y variable if we multiply the bottom equation by negative 1. That makes this a plus y and a plus 1. So the problem is you can't really combine an x squared and a 2x into a single term, so you've got to keep them as separate. X squared minus 2x. The y's are going to cancel. Negative 1 times negative 1 is 1. 1 plus 2 is 3. If you subtract the 3 over, this results in a simple quadratic equation. X squared minus 2x minus 3 equals 0. That factors into x minus 3 times x plus 1, so x equals 3. And x equals negative 1. Now we got to go figure out what y equals. So if I rearrange this bottom equation as y equals 2x plus 1, if x equals 3 and I plug that in for this x, 2 times 3 is 6 plus 1 means that y is equal to 7. If x is equal to negative 1, 2 times negative 1 is negative 2. Negative 2 plus 1 means that y equals negative 1. So the two solutions are 3, 7, and negative 1, negative 1. If you are really feeling ambitious, you could visualize what's happening here graphically. This bottom equation is just a straight line with a slope of 2. This other equation here is just y equals x squared minus 2. So that's a parabola. Like that. So we have an intersection point there of negative 1, negative 1, and an intersection point there of about 3, 7. If I were to graph that a little more carefully, that's what's happening there. Okay, question 25. We have to graph the solution of the system of inequalities. That means we have to find out where the shaded regions of these inequalities intersect each other. So the bottom one is just a straight line, x plus 3. The plus 3 is the y-intercept. The slope is up 1 over 1, up 1 over 1. And it's a solid line because it's greater than or equal to. And to figure out where to shade, it's always best just to choose a test point. So I'm going to choose a test point of 0, 0, and plug in a 0 for x and y. That leaves a statement of 0 greater than or equal to 3. That's not true, which means you don't shade towards a test point. This would be shading away from the test point. Now the top inequality, 9 minus x squared, and changes into negative x squared plus 9. The plus 9 moves the graph up 9 units. The negative sign flips it upside down. So it's a parabola that's up 9 units, but upside down. And it's a dotted parabola because it's just less than and not less than or equal to. And to figure out where to shade on this one, again choose a test point of 0, 0. So if x and y are both 0, we get an expression of 0 is less than 9, which is true. That means we need to shade towards a test point. So we're shading inside the parabola. So the double shaded region would be that little region right there. That's the solution to the system of inequalities, but it also says find the coordinates of all the vertices. The vertices are where the actual graphs intersect, so we need to find the location of these 2 points. To find the location of vertices, you treat this as a system of equations instead of a system of inequalities. So we have y equals 9 minus x squared, and we have y equals x plus 3. Well, if y is equal to x plus 3, then we can make a substitution because that y also equals x plus 3. So we have x plus 3 equals 9 minus x squared. I'm going to move the x squared to the left side of the equation by adding. So positive x squared plus x, and then I'm going to subtract the 9 over to get it equal to 0. So I get a minus 6. And then factor, do x plus 3. X minus 2, which gives me an x value of negative 3 and an x value of 2. Now we can use this equation here for y. If x is negative 3, then y is 0, and we expected to find that point right there, negative 3, comma 0. If x is 2, 2 plus 3 means that y is equal to 5, and that looks about right. So those are the location of the vertices, or the coordinates of the vertices. Okay, question 26. This is linear programming. It was part of section, or towards the end of section 5.5. There are two types of bats, and the process here is making the bats, and so the variables represent how many bats are being made. So we can let x equal the number of Homer bats. We could let y equal the number of, what is this, timber. But an objective function here is if we have profit and we're making bats, the objective would be to find a maximum profit. That's what's being asked right here. How many of each type should be produced in order to maximize the profit? So in order to figure out what the profit is, we need to figure out how many bats are being made. Now there's X number of Homer bats and Y number of timber bats. You make $17 in profit for a Homer, and you make $29 in profit for a timber. If you add the two together, that's going to give you your total profit. So there's your objective function describing profit. Now the system of inequalities that describes the constraints. The constraints are what limits the amount of production here. So there's only a limited number of hours in the day, and man hours, and time on the equipment, and things like that. So the x represents a number of Homer bats, and it has to be greater than or equal to 0. You can't produce a negative number of bats. Same thing for y. Y has to be greater than or equal to 0. So that means we're going to be graphing just in the quadrant right here in the top right. But we also have other constraints. We have a constraint on trimming and turning. So trim and turn, the constraints are it takes 8 hours to trim and turn the Homer bats. It takes 5 hours to trim and turn the timber bats, and the total amount of hours available for trimming and turning is 80 hours. So the combination of these two bats has to be less than or equal to 80 hours, because that's how many hours are available for trimming. And then we also have a constraint on finishing. It takes 2 hours to finish a Homer bat, and it takes, let's see, 5 hours to finish a timber bat, and the number of hours available for trimming or for finishing is 50. So now here for part D, we're graphing the system of inequalities. You don't graph the profit function, you graph the constraints. So starting here, if I want to find the x-intercept, I can let y equal 0, divide both sides by 8, and we get an x-intercept of 10. So the x-intercept for that one is 10. Now, if we let x equals 0 to find the y-intercept, 80 divided by 5 is 16, so the y-intercept there is 16, which is, let's see, about right here. Now if we connect there, now this is an inequality, so you got a shade. If you let x and y both equal 0, choosing a test point there of 0, 0, you end up with 0 is less than or equal to 80, which is true. So you're shading underneath there. Now for the other one, if we let x equals 0 to find the y-intercept, 50 divided by 5 is 10, so the y-intercept is 10. And then if we let y equal 0 to find the x-intercept, 50 divided by 2 is 25, so the x-intercept is 25, way out there. And if you choose the same test point, you would find that we're also shading underneath towards the test point. So the double shaded region is this region right here. Once you've identified what's called the feasible region or the double shaded region, you need to identify the vertices. That's this point, and this point. So we have 0, 10, we have 10, 0, and then this point right here can be found, since it's the intersection of two graphs, and the graphs came from these inequalities, the intersection would be the solution to the system of equations. So if we multiply it here by negative, we're going to get 6x, the y's are gone. 80 minus 50 is 30, so x equals 5, so we know it's 5 something. If you choose, one of these, I'm going to choose the top one here. If x is equal to 5, 8 times 5 is 40. If you take 40 away from 80, you get 5y equals 40. Divide by 5 means that y is equal to 8. So that's the point 5, 8. So we've got 3 different points that we need to test in our objective function. We need to find the profit if you make 0 homers and 10 timbers. You need to find the profit if you make 10 homers and 0 timbers, and you need to find the profit if you make 5 homers and 8 timbers. So if you plug each of these values into the objective function here, 17 times 0 is 0, 29 times 10 is 290, so you get a profit of $290. If you use this one, 10 times 17 is 170, 170 plus 29 times 0 is $170. This one here, let's see, 17 times 5 is 85. And then 29 times 8 is 232. So this results in a profit of 317. That's the maximum profit. So in order to maximize the profit, you should make 5 homers and 8 timbers.